Question number 1. Figure show 5 different systems, each containing 6 identical masses, 3 of which are placed at the vertices of an equilateral triangle, and the other 3 are held firmly close to this. All the masses lie in the same place. If all the forces acting on the system except the gravitational forces among the masses are negligible. In which of the configurations the masses are mostly likely to be equilibrium? We can consider that for the equilibrium mass separation, the spaces of mass should be uniform. It means mass separation should be symmetric. When considering symmetric in given figures, we can consider that third answer is the correct answer because of there is a uniform mass separation, symmetric mass separation in the third configuration. Then answer is C for the question number 1. Then question number 2. A particle of mass m lies at the center of uniform circular ring of mass m and radius r. The magnitude of gravitational force acting on m due to capital M. In given figure, there is a ring like this, and mass of ring is capital M, radius is capital R. There is a particle in at the center of the ring. Mass of the particle is simple m. We know that gravitational force on simple m should be in all directions. Therefore, there is no resultant gravitational force. Then we can get answer is 0. It means first answer is correct answer for the question number 2. Then question number 3. Two planets X and Y have masses capital M and Mx and My, and Rx and Ry it should be radius respectively. If the acceleration due to gravity on the surface of two planets are same, then the ratio of Mx Ry squared divided by My Ry squared is. They have given that there is the same gravitational acceleration on the planet, on both planets. Then we can write gravitational acceleration, simple G naught. It means gravitational acceleration on the planet should be equals to Gm over R squared. Capital R means radius of the planet, capital M is mass of the planet, and capital G is universal gravitational constant. Then we can get gravitational acceleration for planet X should be equals to gravitational acceleration for planet Y. Then we can get G mass of X divided by radius of X squared should be equals to G mass of Y divided by radius of Y squared. Then we can cancel out G and G. Now we can subject given expression. They have given that Mx Ry squared divided by My Rx squared. We can get My term to this side and Ry squared to this side. Then answer should be 1. Then second answer is the correct answer for question number 3. Question number 4. The capital M and R are the mass and radius of the planet, mass respectively, and G is the universal constant of gravitation. The acceleration due to gravity at the surface of mass is, we can get directly acceleration due to gravity on the planet. G naught should be equals to Gm over R squared. It means gravitational force per unit mass. Gravitational force per unit mass, we can get Gm over r squared is the answer. Then third one is correct answer for question number 4. Question number 5. The weight of an object on the Earth's surface is 600 Newton. At a height of 1 Earth radius above the Earth's surface, the weight of the object will be. We know that weight means gravitational force. We can write gravitational force 600 on the Earth's surface. We can write gravitational force G, mass of Earth, mass of object, divided by square of Earth radius. Because of when considering that the object is placed on the surface of Earth, it is like this. Distance between two objects equals to radius of Earth. Now we have to consider for the second situation, the object should be placed at r height from the Earth's surface. It means this total height should be 2r. Total distance from center of gravity of Earth to object is 2r. Now we can write, we have to find the gravitational force. I will consider it as F. G, mass constant, mm. Now distance is 2r, then 2r squared, 4r squared. Then we can divide both the equations. We can cancel out terms. 600 divided by F equals to 1 divided by 1 over 4, it means 4. F equals 600 divided by 4, 150 Newton. Then we can get first answer is correct for the question number. Then question number 6. Assume the moon is a sphere of radius r with g as the acceleration due to gravitational at the surface. If the universal constant of gravitation is g, the mean density of the moon is given by. The gravitational acceleration on the surface. I will write the equation for the gravitational acceleration on the surface. G equals Gm over r squared. Now I will subject mass. Mass equals gr squared divided by capital G. Now we have to get the distance, get the density. Density equals mass divided by volume. We can substitute mass gr squared divided by capital G. Volume of a sphere 4 over 3, 5 r cube. We can get 3 to the numerator. Then we can cancel out 2 r terms and we can get density 3g divided by 4 5 gr. Then answer is 5 for the question number 6. Question number 7. The radius of Earth is r and g is the acceleration due to gravity at the Earth's surface. The gain in potential energy of an object of mass m placed from the surface of the Earth to a height r is. We can write the equation for the potential energy. Potential energy at Earth's surface minus gmm over r. And we can write, we know that gravitational acceleration at the surface is Gm over r squared. Therefore, we can change potential energy equation. I will multiply numerator and denominator by r. Then this term is simple g. Simple g means gravitational acceleration. Then E equals minus Gm r. When the object is placed at r height, I will consider potential energy is E dash equals minus Gm m over 2r. Again I will multiply both terms by capital R, numerator and denominator by capital R, minus Gm mr over 2r squared. Then this term is simple G, then minus Gmr over 2. Now we have to consider change of gravitational potential. Change of gravitational potential energy, we have to subtract these two values. Then subtracting these two values, we can get change of gravitational potential of Gmr. Then answer is 2 for the question number 7. Question number 8. A geostationary satellite, capital A, moves in an orbit radius RA. Another geostationary satellite B has twice the mass of A. The orbit radius of satellite B. The period of a geostationary satellite should be equal to the period of rotation of Earth. Then for the A and B satellites, there is the same period, and therefore there is the same angular velocity. We know that period is 2 pi divided by omega. There is the same period for both satellites, then omega constant. We have to get the radius of orbit. We can use, if the orbit of satellite is like this and Earth is this one, then radius r. We can use F equals ma towards the center. Centripetal force is given by gravitational force Gmm over r squared. Capital M is the mass of Earth. M, we can substitute A, centripetal acceleration, V omega squared r, or V squared over. Now I am trying to get the relationship with angular velocity. Therefore, I will substitute this part, omega squared r. Now we can cancel out m term, and I will subject omega Gm over r cube root. Angular velocity is depending on universal gravitational constant, mass of Earth, and radius of orbit. Therefore, it is not depending with mass. They have given that satellite B has twice mass of A. It is not depending to the radius. Therefore, orbit of radius of B also should be equal to RA. Then answer is 1 for the question number 8. Then question number 9. The mass and radius of Earth is m and r respectively. The escape velocity of a rocket of mass simple m on the Earth's surface. I will derive an equation for the escape velocity. Escape velocity means minimum velocity required to escape from Earth's gravitational field. It means if the escape velocity V, it means velocity given at the surface, velocity at infinity should be 0. Now, we can use conservation of energy between this A point and B point. We know that gravitational potential energy at A, GM over R. R means radius of Earth. It is the distance from center of Earth to the surface. Plus kinetic energy half mv squared, it should be equals to potential energy at B0. You know that potential energy at infinity should be 0. Kinetic energy at B also 0. Then I will subject V. Half mv squared equals gmm over R. We can cancel out m terms. Escape velocity is 2gm over R root. 2gm over R root. Then answer is 1 for the question number 9. Question number 10. The mass of Mars is 0.1 times of Earth. The distance between Sun and Mars 1.5 times the distance between Sun and Earth. The ratio gravitational force of attraction between the Sun and Mars to the gravitational force of attraction between Sun and Earth is. We know that gravitational force is Gm m over R squared. I will consider this one for the Earth. Then gravitational force between Sun and Mars, G, capital M means mass at the center, it means mass of Sun. Simple M is the mass of Earth. Now we have to use mass of Mars. It is 0.1 times of Earth. Then 0.1 m. Distance 1.5 times distance. 1.5 times R. Now we have to divide both the equations. We can cancel out same terms. F divided by F dash equals 1 divided by 0.1. We have to divide again 1 square of 1.5. 15 into 15, 225. We have to separate 2 decimal places. Now answer is 22.5. But they have given answer without simplification. Then we have to use 1 divided by 0.1. Again we have to divide by 1.5 squared. It means it should be like this. Answer should be 5 for the question number 10.